Okay, thanks for sending your work and the problems. I've gone through and corrected them a little bit already just to save time, but let's go through each of the problems. So for this first one, when you began solving this equation from standard form into slope-intercept form, when we subtracted ax from both sides, we forgot to include this negative sign. So you're going to want to fix that. Now, when you came down here in part A, it asks you to write the equation of a line M that's perpendicular to line L, the one that's listed here that we've been working with. So we have to remember something. We have to remember this equation, which is that the slope of a perpendicular line is equal to the opposite of the reciprocal of the slope that we're perpendicular to. So in this case, let me give you a quick example here. So if let's say that L had a slope of 3, then a line perpendicular to L would need to have the opposite reciprocal, or negative 1/3. So if the slope of our line is actually negative a over b, then the slope of our perpendicular line is not going to be a over b. So that you're going to want to fix that. Other than that, the work here, you're doing pretty good. Obviously, you're going to need to redo this work with the correct slope. For B, again, you've got the right idea. You just need to fix these errors and just be real careful with the math. I will tell you that this problem, just think it through carefully. There is a lot of just being really careful with your variables here. The answer is not going to condense and it's not going to simplify to something really nice. So don't get scared if it starts to look a little messy. And then for C, just a heads up, really all you're doing for C is using the distance formula. So look up the distance formula. Don't get scared by how many variables and symbols you've got. It's just a straightforward application of the distance formula. Okay, so I'll leave it at that. You try that. If you have more questions, let me know. Okay, so let's take a look at 35. Now actually, 35A, you did exactly right. Everything you did here is very nice. We just need to have a little bit of clever intuition for B and C. You've got the right idea. We're going to make the substitution and then we need to try to simplify. Now for B, you've made the correct substitution, and for C, you've made the correct substitution. So all we need to do is simplify. For B, what I suggest is we need to get rid of these terms that are 1 over x because they're really making it difficult to simplify this rational expression. If you multiply the top and the bottom of this entire expression by x, you're multiplying by 1, so that won't change its value. And when you distribute through, that's going to simplify this term. So that'll help a significant amount. And then C has almost the exact same problem solving strategy. We're going to multiply by x over x on this term to get rid of the 1 over x. And then because we have a bunch of separate fractions, we're going to have to go through and try to combine all the fractions using like denominators to get one big fraction. So you want to try B and C using those hints there. But you've got the right idea there. So I think you will be able to do that one just fine. All right, so let's talk about this block of questions. Now this block of questions comes from the part of the Stewart book that was about using your graphing calculator. So you're actually free to use your calculator. Okay, so let me do 20 here real quick. So what I want to do is I want to solve this problem. Now, there's two ways I could do it. I could graph these two functions and find where they're equal to each other, which would be an intersection, or I could solve this and figure out where this function is equal to 0. Either one would be fine. Let me show you the intersection. So I'm going to go to my graphing calculator and I'm going to enter these two equations. So we've got x to the third, and then we've got 4x minus 1. And I need to see where they intersect each other. Let's try a zoom fit real quick. Let's see if it finds the point of intersection for us. It's not very clear. We might want to zoom in a little bit. Looks like it's somewhere. Looks like it's somewhere near the origins. We'll try to zoom in there. Looks like we might actually have more than one intersection. So we're gonna have to fiddle with this window a little bit. I'm gonna go back to the zoom fit, and we'll need to be a little bit more purposeful about picking our window. Yeah. So you see there's one intersection here and there's one way up here. So we're going to take our window. We're just going to make the X and the Y go a little bit farther. So let's see if we go to 2.5 on the X. The Y is going to need to come up a little bit more too. So we'll go up to 10 maybe. I'm just kind of guessing here. There we go. So we can see this intersection and that intersection. Now I'm guessing there's probably another intersection down here. So let's take a look at that. Let's expand the window more in the third quadrant as well. So we're going to want to go to, let's say, negative 2.5 and negative 10. Let's see if that gets us close. Yep, so we can see we've got another one down there. Okay, now I'm going to just show you how to do one of the intersections. So I'm going to go to Calc, which is second, and then this button. Do it one more time. There we go. And intersect. I'm going to tell it the two equations that I want to find the intersection of. So I've got the blue one and the red one. And then I'm going to just move the cursor close to where I see the intersection is. And then it's going to provide me with an answer. Okay, so that would be one of the three answers for 20, but you can use the same technique for 19 and 21. Now, just a word of warning for 21, sine x, any trig functions, you've got to make sure that you're in radians. So you would want to press mode and then switch into radians before you start graphing in 21. All right, so I'll leave you to that. Let me know if you have any questions. 25, you did a really good job on. Now, you wrote t here, but if we look back at the example 2, we can see actually the equation you're using was not for time. Time is here. It was for the amount remaining after a certain number of half-lives or an expression of time. So that would be the amount. Now, for B, we want to find the amount, the time when there's 1 gram remaining. 1 gram remaining is an amount, so that means that we want to actually set the equation in A equal to 1 gram. This is the amount, so we're going to set this equal to 1 and then solve for T. Now, the book gives you an example of solving graphically for T by graphing your exponential function and what it's equal to. In this case, it was equal to 1 gram. Now, obviously, this is for a different problem, so the answer is going to be different. But you can use the exact same graphical technique that I showed you in the last problem to find the intersection again. And that's where this equation is equal to 1, the amount that we're interested in. So you can try that out. You're going to use your graphic calculator to solve that one. And let me know if you have any questions. And it looks like that's it.